Hello, everybody. Today, we're going to be talking about our image recognition program in Python, utilizing Python, Flask, Prometheus, Grafana, and Google Cloud Logging. Our team consists of William, Ishna, and myself, Nick. When the user goes to our web page, they're presented with an award-winning design, as seen on the right side, that is composed of major components such as HTML, Jinja, Python, Flask, Waitress, and RabbitMQ. On the HTML and Jinja side, we have a very basic template that has a couple of text fields, a file dialog box, a file upload box, and a couple of Jinja pass-through variables. These are great because our Python backend can make variables and send them over and get them incorporated into our HTML and re-rendered in real time for the user. So as an example, when you upload, we can send back a variable declaring if the upload was successful or if a bad file type was presented. We also have an image variable so that as soon as the user uploads a photo, it is re-rendered in real time for them to see. And also our CNN prediction that will guess if it's a dog or a cat that has been uploaded. This is passed by our RabbitMQ message broker, which we'll talk a little bit about in a little bit. The major components of our site are used by Flask and Waitress. Flask is a Python module that allows developers to design web applications using Python backends, and it works in conjunction with HTML. It combines various libraries, modules, and extensions that deal with most of the heavy lifting of the web portion so that the developers can focus on their Python part. This is evident as Jinja because I didn't have to set it up and it just integrated perfectly. It's used in combination with Waitress, a web server gateway interface, which defines how a web server communicates and processes requests within our web application. And as such, the name suggests, it serves up our web page. Our highlights for our Python Flask backend are the Google Cloud storage part. In order to upload photos, we needed to make sure that we had the proper permissions. A Google Service account with proper permissions was created, and a Google API was created via the Google Cloud website. This API key was downloaded as a JSON file and is then loaded into our Python application via a Kubernetes secret. This is to ensure that if anyone actually gets our Docker image, they don't also get the ability to our Google Cloud storage. I'll talk a little bit more about how we integrated that in our YAML file shortly. Once we get the HTML file dialog box information, such as the photo, we can then create a cloud client and get our bucket. We can then create a blob and upload our image to that blob on the Google Cloud side. We can then get a URL and send that URL to our CNN application through our message broker. Once everything has been submitted and we have received everything back, we can then issue a command to re-render the index.html with the appropriate variables. In our YAML file, we created a secret for our Google Service Account API. We created a value for that API key. We added that JSON file to that value, and then we mounted that value to Etsy GCP on the Docker. That then allows us to access it and decode it with base64 and load it into an environment variable so that we can use it in our application without exposing that to everybody in the internet. This allows us to upload our photos from our web interface to our Google Cloud storage and make them available to the public, especially for easy access to our CNN application. This is all handled with our message broker, RabbitMQ. RabbitMQ handles the communication between Python and the CNN backend. The web interface will send the photo URL to the CNN backend, and the CNN will send its prediction to the web interface. The setup on RabbitMQ was relatively simple, as it is deployed on Kubernetes, and a secret is made containing a password. It is then integrated into our Python applications via the same way that we did the Google Service API by making environment variables from our Kubernetes secrets, and then we have to make receive and send functions. In our web server, the rabbit send function sends the URL of the uploaded photo to our CNN backend through a queue called web. We then can wait for a reply from the CNN application on our receive function on the queueCNN. Because we didn't want to hold up the entire Python Flask interface while we wait for a reply, we spawned off a thread which waits for the CNN reply, and then once it is handled, it goes appropriately to the next step. So as an overview, the photo is uploaded. On the right side, you can see my dog Dexter was uploaded. The URL is sent to the CNN using a RabbitMQ. The CNN processes that photo. It comes up with a prediction and sends it back through the message broker. The web interface then gets that prediction, puts it into a variable, re-renders the template, and shows, I guess it is a dog, which it was correct. The template is updated and everything works as intended. I will now pass it off to Ishna to talk about how the CNN backend works.
Thank you, Nick. Hello, everyone. Let me take you to the backbone of our project. So we are dealing with the convolution neural network. How this works is that we feed some of the input values in the front, which is transmitted in the forward direction, and any error that is generated, that is propagated in the backward direction. Hence, it is known as feed forward and back propagation neural network. So convolution, because we are dealing with the images. We have gathered the data and we have divided into the training and validation, and each one has the images of cats and dogs, as you can see. And similarly with the validation, we have cats and dogs and images. Then initially what we were doing, we were using TensorFlow for developing the neural network. We had around 8,000 images, which belong to two classes, which are, one is cat and one is dog. Another is the test set data, which had 2,000 images, which we use for validation as well. This is our model. We have a sequential model. We have added some of the layers, and then we have compiled the model, and we have performed the training or the fit function over here. We were able to perform it. Now, next is we were trying to make the prediction. So like you can see, this was the image that we sent. It was an image of dog, and we got that this is a dog using a neural network model. And we use this convention of cat 0 and dog is 1. We got the output of 1. Similarly, we used one more image for cat, and we see that we got the output of cat. So while doing this, we realized that it was when we were doing it on the cloud, we had a lot of dependencies, and for every prediction, we had to run the whole system. That is, we had to perform the training, this thing, and this was taking a lot of time. So we thought, okay, we should come up with something efficient and less time consuming. So we came up with this. We trained the model, and then we saved the model in the JSON file, and we have saved the weights in the model.h5 file. And this is what we have saved in here. You can see that model.h5 and JSON file, and then we perform only the prediction thing in here. So which is this train model.py file, the Python file. We have loaded the JSON file and the image file in here. And for every prediction, we don't have to repeat the training process. We were just calling the images, whichever we have to do. And we were printing it's a dog or it's a cat. As you can see that we had this file. We were just choosing an image, this one, and open and then upload. And then see, it gave us the output that I guess it is a cat. From here, I'll be handing over to William.
All right, yeah, I can go and talk about our DevOps CI/CD automation. For one, we start off with GitLab. Kind of early on, we wanted to go to that and start doing our code development in there. I'm personally work a lot in DevSecOps. We use GitLab for that, so it's pretty comfortable for me to work from this and be able to help us get up to speed for our automation. So we use that because it has good pre-use of public runners. Uses YAML, which it's an easy enough language to learn, although it can be complicated with a lot of the specific scale it does. But and we can also automatically run your pipelines on commits, which is the default. You can also change that if you really wanted to with those rules, but regardless, we also utilize the integration with Kubernetes so that it allows, so we can bring in our Google Cloud or Google Cluster rather to work directly in GitLab pipelines. So we can do a kubectls within our pipelines. And I'll actually demonstrate that here in a minute. And then lastly, there's also a CI/CD variables you can use, which can be masked so that if it's sensitive data, like some verification, some authentication, it can be masked in the logs. So if there's some sort of failure in the scripts, it doesn't automatically just show your secrets in there. It'll be showing up as masked. And then at the bottom here, we can actually see what we have our cluster connected to GitLab. It's just a container you kind of run, and it connects it over. So our automated builds, this is one of the first steps we took, was kind of making sure we have an automation part for our builds and getting that out to our cloud registry. So we just have a basic Docker file that's as modular as we can make it. It just takes in a lot of arguments and variables that we feed it from our GitLab YAML, and from there it's will build out our services. So we kept it as simple as possible here to make it reusable. We have a basic job, or a base job rather, in our GitLab that will be used for both jobs. So it's kind of like a parent, and you have the children that have their overrides. So we don't need to, since we're doing Docker builds, they're all basically the same. We just want to change some things here and here. So we changed over the service arguments. So we actually want to bundle in the container. We change over the install arguments, what the dependencies we need, and also how we start the containers. So that's just 3 variables we set in these separate jobs, and it uses the one main job from the parent for everything else. This allows for a lot of reusability. And then directly after that, we publish that into our Google Cloud Registry. And then our deployment job will actually feed off of these. So there's a last step in that build part that will create some files that we send as job artifacts, send that over to our deployment now. And from that, we feed those values that come from that, which are just the exact location of those containers or that we just built. We place that into our environment variables here. And on line 42, you can actually see that we take our generic deployment module or deployment YAML. We have some variables set in there that if you try to run by yourself, it would not work. But instead, we go through and take that, feed it into an insubst function that will find any variables on your system and match that to ones in the file and change that over. And we feed that output directly over to our kubectl. So our latest images are always being guaranteed to run in our deployment. And we can see at the top of there, or like beforehand, we have 3 pods running, and after the fact, we have 3 that are terminating, while another one is starting to pop up, and more after that. So we're able to directly deploy automatically every time. And then as far as auto scaling goes, we were able to get instance auto scaling going, so the node pools, as well as the HPA, so we can properly scale out our hardware as well as the actual software. And I can go ahead and demo that real quickly in a video that I pre-recorded because it kind of takes a little while to get going. So to start off with, we just have 3 nodes in our cluster currently running. The page wasn't refreshed from a previous there, but yeah, refresh it here. Yeah, so we have 3 nodes that are currently running. And then we also have just 3 pods that are running in our deployment. So our web server at the very bottom there is the only one that we really kind of care about. It has 3 of those running. So we have I go ahead and go on my desktop. I have 3 just Linux subsystems that I go through and ping out our server, which are it's just pinging our web server in this case. It's just pulling that down. It's doing a load generator. It's very similar to what we showed in class, actually. Let's start 3 of those to really kind of push the limits on here. And kind of wait for it to start kicking in and showing up in our monitoring. I'm going to fast forward here while we get through that. So now we can actually see, back up a bit, we can see that we have 3 new pods spinning up that are unschedulable currently. So right now we don't have enough CPU utilization or CPU availability to utilize this, which will actually be shown right here. So yeah, we don't have enough CPU. for these pods to be able to spin up. So our automation will actually automatically spin up a new instance here. So yeah, we have one that's currently spinning up. Give this another second and it will be starting up. So we have it up and running now. And we should now see that our containers are actually creating. So we have enough availability and it's starting to actually create these and pull them down and set them up. So we're good to go. It shows that we went from 3 nodes to 4 and from 3 pods to 6. We can go up to 5 nodes and then up to 12 pods. But we would need to get more more load going to it. So since it's not like a complex application, so I go ahead and end all the over the load generation going on here, and we'll skip to where it starts to actually load back down. So closing that out. Let's see. All right. Oh yeah, it's actually starting to delete this node right here. So this one's going down. It's going back down to 3 nodes. Yeah. And then it takes a little while longer. I'll go ahead and skip again ahead. See, those pods are currently unschedulable because there's not enough CPU availability. And eventually figured out we don't actually need that many anymore, and it's starting to terminate them. So the last little refresh should show that we're down to 3 nodes or 3 pods. Yeah, so now we're good. We went back down from 4 to 3 on the nodes, and then from 6 to 3 on our actual deployment. So that successfully demonstrates that we have the auto scaling working up and running. So for the logging, we actually went ahead and used Grafana, Prometheus, Jaeger tracing, and Google's cloud monitoring, besides just going with the default Google cloud monitoring. So we went ahead and set up some dashboards in here, just kind of mess around and see all the different things we can do. For the top part, we kind of really pay attention to the overall cluster CPU and memory utilization. We have the cloud storage monitoring. We can see our specific containers usages. So we have Prometheus in here and our auto scaling and all that. So we have a lot of things we can go through monitor. We just kind of set up to mess around with. You can also just use a code to import pre-existing dashboards like this Google Cloud one. So we can really easily just bring in new ones to customize. And another cool feature is creating a playlist. You can actually run all of these on a TV monitor and have it go through in a nicely scaled way. To move on to the billing, the top cost was a compute engine and followed by the Kubernetes engine, which is kind of a surprise. We kept the cluster up and running, just kind of be able to see this experiment as it went along. We just had the $300 credits you can apply for free. So we wanted to build test out that and see how far it went. Cloud storage we didn't use but 7 cents. And that was with a peak of probably 30 gigs usage with all the containers before we cleaned it up. For Cloud Tech, we have a list here that kind of already covered. And then for the discussion, the second choice project we would go with would be a chatbot. And the choice of technology would be actually different here because there's already existing APIs that can be used through GCP, for example.
Yeah, so for the challenging part of the storage was when in the starting we had to store around 10,000 images. So that was taking a lot of space. Another was getting the dependencies on the cloud. So all the machine learning dependency that was giving us a hard time in there. So with the second model that we came up, we were able to pass through it. The other was every time we were opening a website, the training process was taking place. So that was taking a lot of time. And another is that how would you extend a project? So we would automate the image processing thing for a website. Another thing is that we would do more of the training on more images and more classes like cows or tigers or something instead of just dogs and cats. And another, I think, Nick.
Yeah, we would definitely change our award-winning design to be slightly better. Going through with it, we also, if we had to re-implement this project from scratch, we'd probably take advantage of some of the Google Cloud native applications for AI and machine learning. And in terms of portability, the Docker file, YAML, Python backend can easily be changed just going through mostly and changing out the Google service bot credentials and replacing that with whatever provider or so that we go with equivalent. In terms of links, here are all of our available code, web server, container registry, and cloud storage. And we also have a QR code that does the same, it sends you to the web server.
Thank you, and hope you all liked our presentation, and you can go ahead and do whatever you want to. We still have $200 more